SSTables and LSM-Trees. In Figure 3-3, each log-structured storage segment is a sequence of key-value pairs. These pairs appear in the order that they were written, and values later in the log take precedence over values for the same key earlier in the log. Apart from that, the order of key-value pairs in the file does not matter. Now we can make a simple change to the format of our segment files. We require that the sequence of key-value pairs is sorted by key. At first glance, that requirement seems to break our ability to use sequential writes, but we'll get to that in a moment. We call this format sorted string table, or SSTable for short. We also require that each key only appears once within each merged segment file. The compaction process already ensures that. SSTables have several big advantages over log segments with hash indexes. Merging segments is simple and efficient, even if the files are bigger than the available memory. The approach is like the one used in the merge-sort algorithm and is illustrated in Figure 3-4. You start reading the input files side by side. Look at the first key in each file, copy the lowest key according to the sort order to the output file, and repeat. This produces a new merged segment file also sorted by key. Figure 3-4. Merging several SSTable segments, retaining only the most recent value for each key. If all keys and values had a fixed size, you could use binary search on a segment file and avoid the in-memory index entirely. However, they are usually variable length in practice, which makes it difficult to tell where one record ends and the next one starts if you don't have an index. What if the same key appears in several input segments? Remember that each segment contains all the values written to the database during some period of time. This means that all the values in one input segment must be more recent than all the values in the other segment, assuming that we always merge adjacent segments. When multiple segments contain the same key, we can keep the value from the most recent segment and discard the values in older segments. In order to find a particular key in the file, you no longer need to keep an index of all the keys in memory. See Figure 3-5 for an example. Say you're looking for the key handiwork, but you don't know the exact offset of that key in the segment file. However, you do know the offsets for the keys handbag and handsome, and because of the sorting you know that handiwork must appear between those two. This means you can jump to the offset for handbag and scan from there until you find handiwork or not. If the key is not present in the file, you still need an in-memory index to tell you the offsets for some of the keys, but it can be sparse. One key for every few kilobytes of segment file is sufficient, because a few kilobytes can be scanned very quickly. I3. Since read requests need to scan over several key-value pairs in the requested range anyway, it is possible to group those records into a block and compress it before writing it to disk, indicated by the shaded area in Figure 3-5. Each entry of the sparse in-memory index then points at the start of a compressed block. Besides saving disk space, compression also reduces the I/O bandwidth use. Fine so far, but how do you get your data to be sorted by key in the first place? Our incoming writes can occur in any order. Maintaining a sorted structure on disk is possible. See BTree on page 79, but maintaining it in memory is much easier. There are plenty of well-known tree data structures that you can use, such as red-black trees or AVL trees. With these data structures, you can insert keys in any order and read them back in sorted order. We can now make our storage engine work as follows. When a write comes in, add it to an in-memory balanced tree data structure. For example, a red-black tree. This in-memory tree is sometimes called a mentable. When the mentable gets bigger than some threshold, typically a few megabytes, write it out to disk as an SSTable file. This can be done efficiently because the tree already maintains the key-value pairs sorted by key. The new SSTable file becomes the most recent segment of the database. While the SSTable is being written out to disk, writes can continue to a new mentable instance. In order to serve a read request, first try to find the key in the mentable, then in the most recent on disk segment, then in the next older segment, etc. From time to time, run a merging and compaction process in the background to combine segment files and to discard overwritten or deleted values. This scheme works very well. It only suffers from one problem. If the database crashes, the most recent writes which are in the mentable but not yet written out to disk are lost. In order to avoid that problem, we can keep a separate log on disk to which every write is immediately appended, just like in the previous section. That log is not in sorted order, but that doesn't matter, because its only purpose is to restore the mentable after a crash. Every time the mentable is written out to an SS table, the corresponding log can be discarded. The algorithm described here is essentially what is used in LevelDB and RocksDB, key-value storage engine libraries that are designed to be embedded into other applications. Among other things, LevelDB can be used in RIAC as an alternative to Bitcask. Similar storage engines are used in Cassandra and HBase, both of which were inspired by Google's Bigtable paper, which introduced the terms SSTable and Mentable. Originally, this indexing structure was described by Patrick O'Neill et al. Under the name Log Structured Tree or LSM-Tree, building on earlier work on log-structured file systems. Storage engines that are based on this principle of merging and compacting sorted files are often called LSM storage engines. Lucene, an indexing engine for full-text search used by Elasticsearch and Solr, uses a similar method for storing its term dictionary. A full-text index is much more complex than a key-value index but is based on a similar idea. Given a word in a search query, find all the documents, web pages, product descriptions, etc. that mention the word. This is implemented with a key-value structure, where the key is a word, a term, and the value is the list of ID of all the documents that contain the word, the postings list. In Lucene, this mapping from term to postings list is kept in SS table-like sorted files, which are merged in the background as needed. As always, a lot of detail goes into making a storage engine perform well in practice. For example, the LSM-Tree algorithm can be slow when looking up keys that do not exist in the database. You have to check the mentable, then the segments all the way back to the oldest, possibly having to read from disk for each one before you can be sure that the key does not exist. In order to optimize this kind of access, storage engines often use additional Bloom filters. A Bloom filter is a memory-efficient data structure for approximating the contents of a set. It can tell you if a key does not appear in the database, and thus saves many unnecessary disk reads for non-existent keys. There are also different strategies to determine the order and timing of how SS tables are compacted and merged. The most common options are size-tiered and leveled compaction. LevelDB and RocksDB use leveled compaction, hence the name of LevelDB. HBase uses size-tiered, and Cassandra supports both. In size-tiered compaction, newer and smaller SS tables are successively merged into older and larger SS tables. In leveled compaction, the key range is split up into smaller SS tables and older data is moved into separate levels, which allows the compaction to proceed more incrementally and use less disk space. Even though there are many subtleties, the basic idea of LSM-trees keeping a cascade of SS tables that are merged in the background is simple and effective. Even when the dataset is much bigger than the available memory, it continues to work well. Since data is stored in sorted order, you can efficiently perform range queries scanning all keys above some minimum and up to some maximum. And because the disk writes are sequential, the LSM-tree can support remarkably high write throughput. BTrees. The log-structured indexes we have discussed so far are gaining acceptance, but they are not the most common type of index. The most widely used indexing structure is quite different. The BTree, introduced in 1970 and called ubiquitous less than 10 years later, BTrees have stood the test of time very well. They remain the standard index implementation in almost all relational databases, and many non-relational databases use them too. Like SS tables, BTrees keep key-value pairs sorted by key, which allows efficient key-value lookups and range queries. But that's where the similarity ends. BTrees have a very different design philosophy. The log-structured indexes we saw earlier break the database down into variable size segments, typically several megabytes or more in size, and always write a segment sequentially. By contrast, BTrees break the database down into fixed-size blocks or pages, traditionally 4 KB in size, sometimes bigger, and read or write one page at a time. This design corresponds more closely to the underlying hardware, as disks are also arranged in fixed-size blocks. Each page can be identified using an address or location, which allows one page to refer to another similar to a pointer, but on disk instead of in memory. We can use these page references to construct a tree of pages, as illustrated in Figure 3-6. Figure 3-6. Looking up a key using a BTree index. One page is designated as the root of the BTree. Whenever you want to look up a key in the index, you start here. The page contains several keys and references to child pages. Each child is responsible for a continuous range of keys, and the keys between the references indicate where the boundaries between those ranges lie. In the example in Figure 3-6, we are looking for the key 251, so we know that we need to follow the page reference between the boundaries 200 and 300. That takes us to a similar looking page that further breaks down the 200-300 range into subranges Roman 2. Inserting a new key into a BTree is reasonably intuitive, but deleting one while keeping the tree balanced is somewhat more involved. Eventually we get down to a page containing individual keys, a leaf page, which either contains the value for each key in line or contains references to the pages where the values can be found. The number of references to child pages in one page of the BTree is called the branching factor. For example, in Figure 3-6 the branching factor is 6. In practice, the branching factor depends on the amount of space required to store the page references and the range boundaries, but typically it is several hundred. If you want to update the value for an existing key in a BTree, you search for the leaf page containing that key, change the value in that page, and write the page back to disk. Any references to that page remain valid. If you want to add a new key, you need to find the page whose range encompasses the new key and add it to that page. If there isn't enough free space in the page to accommodate the new key, it is split into two half-full pages, and the parent page is updated to account for the new subdivision of key ranges. See Figure 3-7. Roman 2. Figure 3-7. Growing a BTree by splitting a page. This algorithm ensures that the tree remains balanced. A BTree within keys always has a depth of O log n. Most databases can fit into a BTree that is 3 or 4 levels deep, so you don't need to follow many page references to find the page you are looking for. A 4-level tree of 4 KB pages with a branching factor of 500 can store up to 256 TB. The basic underlying write operation of a BTree is to overwrite a page on disk with new data. It is assumed that the overwrite does not change the location of the page, i.e. all references to that page remain intact when the page is overwritten. This is in stark contrast to log-structured indexes such as LSM-Trees, which only append to files and eventually delete obsolete files, but never modify files in place. You can think of overwriting a page on disk as an actual hardware operation. On a magnetic hard drive, this means moving the disk head to the right place, waiting for the right position on the spinning platter to come around, and then overwriting the appropriate sector with new data. On SSD, what happens is somewhat more complicated, due to the fact that an SSD must erase and rewrite fairly large blocks of a storage chip at a time. Moreover, some operations require several different pages to be overwritten. For example, if you split a page because an insertion caused it to be overfull, you need to write the 2 pages that were split, and also overwrite their parent page to update the references to the 2 child pages. This is a dangerous operation, because if the database crashes after only some of the pages have been written, you end up with a corrupted index. For example, there may be an orphan page that is not a child of any parent. In order to make the database resilient to crashes, it is common for BTree implementations to include an additional data structure on disk, a write-ahead log WAL, also known as a redo log. This is an append-only file to which every BTree modification must be written before it can be applied to the pages of the tree itself. When the database comes back up after a crash, this log is used to restore the BTree back to a consistent state. An additional complication of updating pages in place is that careful concurrency control is required if multiple threads are going to access the BTree at the same time. Otherwise, a thread may see the tree in an inconsistent state. This is typically done by protecting the tree's data structures with latches, lightweight locks. Log-structured approaches are simpler in this regard, because they do all the merging in the background without interfering with incoming queries and atomically swap old segments for new segments from time to time. As BTrees have been around for so long, it's not surprising that many optimizations have been developed over the years. To mention just a few, instead of overwriting pages and maintaining a WAL for crash recovery, some databases like LMDB use a copy-on-write scheme. A modified page is written to a different location, and a new version of the parent pages in the tree is created, pointing at the new location. This approach is also useful for concur. This variant is sometimes known as a B+ tree, although the optimization is so common that it often isn't distinguished from other BTree variants. Rency control, as we shall see in snapshot isolation and repeatable read on page 237. We can save space in pages by not storing the entire key, but abbreviating it. especially in pages on the interior of the tree. Keys only need to provide enough information to act as boundaries between key ranges. Packing more keys into a page allows the tree to have a higher branching factor, and thus fewer levels. Roman 3. In general, pages can be positioned anywhere on disk. There is nothing requiring pages with nearby key ranges to be nearby on disk. If a query needs to scan over a large part of the key range in sorted order, that page-by-page layout can be inefficient, because a disk seek may be required for every page that is read. Many BTree implementations therefore try to lay out the tree so that leaf pages appear in sequential order on disk. However, it's difficult to maintain that order as the tree grows. By contrast, since LSM-Trees rewrite large segments of the storage in one go during merging, it's easier for them to keep sequential keys close to each other on disk. Additional pointers have been added to the tree. For example, each leaf page may have references to its sibling pages to the left and right, which allows scanning keys in order without jumping back to parent pages. BTree variants, such as fractal trees, borrow some log-structured ideas to reduce disk seeks, and they have nothing to do with fractals.